one to do. So type 3, that's one that most people have difficulty with. So again, those of you coming in late, my name is Mr. Stringham. This is the agenda we're going to follow today. So I'm going to go ahead and get right into the intro of what we're going to kind of get up to speed with, and that's on heat transfer. I need to talk a couple things about that, heat transfer, just to make sure we get up to the refrigeration cycle. Latent sensible heat, superheat and subcooling, because there will be 2 questions on almost every test about superheat and subcooling. And then the pressure temperature chart. You're going to have to answer at least 3 or 4 questions using the PT chart. So I got to make sure everybody's comfortable with the pressure temperature relationships and what I mean by saturation, and then the basic refrigeration system. So I don't need to really talk a lot about the milestones in history. The big thing that you need to know is that we started out with ice, and then they had these chemicals that they started to use that were man-made, that had the substance chlorine in it. You might have to slide the table over. And then right in here in the 90s is when they started regulating the use of those refrigerants. So they noticed that there was a problem with the environment, with the ozone, and they had a problem directly related to the production of the refrigerants they were doing. So the refrigerants they were making, they figured out, were causing the problems with the environment, specifically a hole in the ozone layer. And they figured out that the chlorine that they were using for all these years was being released into the atmosphere and causing that problem with the ozone layer. So right around the mid-90s is when they started mandating that everybody that works with refrigeration equipment has got to be certified. You got to have some sort of card that shows that you can work on specific types of appliances. And the types range from anything from a window unit and a water cooler, anything with 5 pounds or less of refrigerant that was charged at the factory and doesn't have a place for you to hook up gauges, that's type 1, to residential air conditioning systems and commercial chillers, which are building systems that you would normally think are type 3, but if their boiling point, they're using R22 or another refrigerant that has a boiling point below 50 degrees, that's what's called a type 2 appliance. Anything that has gauges where you're hooking up the lines, like a split system, a package unit for commercial applications like in strip malls, it has over 5 pounds of refrigerant. Usually those are 5, 7.5, 10-ton units. Those are all type 2 appliances. And type 3, specifically for the test, just deals with 2 refrigerants. R11 and R123. Both those refrigerants have a boiling point above 50 degrees, so they're considered low pressure refrigerants because their refrigerant state at normal room temperature, about 70 degrees, is still a liquid, which is odd for most of the refrigerants. Most of them have a boiling point of below 0, and they evaporate almost instantaneously, which is why you don't see a lot of R134A or R22 lying around, especially in liquid form. So, because it just doesn't exist really unless it's under pressure. So these are all the milestones. It's kind of where we're at today, which is why you're here. Pretty much talking about the types of systems here. So the temperature that we're trying to get to for medium temperature systems is 35 to 40 degrees. And then anything between 0 and -20, like freezers, ice cream, you're going to go and find what we call a low temperature application. And then high temperature application is what we're talking about with our air conditioning, comfort cooling, process cooling, things like that. So air conditioning mode. And that's around the range of 50 to 75 degrees, somewhere around there. Talking about summer heat gain, this is a basic law of thermodynamics. It's actually the second one. The first one is heat and energy are mutually convertible. But the second one says that heat will always flow from warmer to cooler. So we got a 95-degree day outside, typical summer day here in DC, and then we got a 70-degree house temperature, which is about the national average, between 70 and 75, somewhere around there. So which way is the heat going to flow? Yeah, it's going to go in the house. So when you have the door open and your mom used to yell at you, hey, you going to air condition the whole neighborhood? Impossible. It ain't happening. All the heat's coming in the house and you're just continuously running that AC because it's trying to balance out. So yeah, heat will always flow from warmer to cooler. So you get that heat transfer, 95-degree air. Eventually it's going to try and warm up the house. And the insulation is going to slow it, but it doesn't stop it. Nothing really stops that heat transfer until it's equal, until they equalize. So eventually it'll equalize out. And then in the wintertime, it does the reverse. So, also, talking about heat flow, hot air flows up, cold air flows down. Before airplanes, what did they use to fly? Balloons, yeah, the balloons. And they worked on that principle. So the first aviation, you know, if you've ever been into the Smithsonian Air and Space Museum, they had a whole section there just on balloons because that was it. They went on that convection principle of they'd heat up the air and the molecules would space themselves a little farther apart, and that would cause that balloon to rise up above the colder, dense molecules. And then they were just dependent on what for direction? Yeah, so they really didn't have that much control. They had to go with whichever way the wind was blowing. And that same principle applies here, which is why in the old ice boxes, they would put the ice cube up on the top, and then they put the food below it, and the hot air, or the hot, the space would rise, the heat would rise up in that space, that conditioned space, cause the ice to do what? Yeah, and then they used to have, back in the day, a little dog bowl there that they'd let the drainage go down and fill the dog bowl. The dog would drink right out of that, and that'd be good. And, what was that service call, though? We'd call the service technician, oh, my food's warm, what's the problem? Yeah, they come in, that's an easy call, right? Yeah, oh, wait a minute, we need to go get you some ice. I got some of that on my truck. In fact, they used to have little signs here in Fairfax County, and a couple of or not here in Fairfax County, but over in Fairfax County, where you hang them on your window. And they had like a thing that said 50, 25, 75, 100, and depending on which way the card was hanging, that's how that iceman knew how many pounds of ice to deliver to your house that week. Yeah, so and some of the air conditioning companies that are in business today actually started out with ice delivery trucks. There's a company in Arlington that started out delivering ice. So, yeah, that was the beginning. That was easy. No refrigeration to that. And then they came out with systems that, they're going to talk about a few other things, but for the test, after they came out with the ice, they came out with refrigeration systems that had these toxic gases, sulfur dioxide, methyl chloride. They're going to have those words on the test. Those are refrigerants that were used in the 30s, the 40s, the 50s. In fact, I had a guest speaker come to the high school and talk to the kids one time, and he actually had a tank of his whole old SO2, sulfur dioxide, that he used as a refrigerant back when he was a service mechanic for the Army. He said when he was in Germany, when he had to go run a service call, it was to a castle over on a hill, and him and another guy had to get in a boat and row the boat over to the castle with his gauges and his torch. And he had an old torch that you pumped up with a canister with the liquid gas, and then you'd have to keep pumping it up to get because it wasn't under pressure, to get the flame out, and it was a very low temperature flame, which means these refrigerants that they were using were very low pressure because they used to be able to get by with just soldering all the joints. Right? So the R12 and some of the refrigerants that they were using in the beginning didn't have a really high side system. I mean, they got up to 100, 120 pounds on the high side, but they didn't require all the brazing and everything that we kind of do today with the higher pressure refrigerants like R120, R22, and R410A. So, but that's kind of where they went with the refrigerator in the 30s and the 40s, and then they came out with the refrigerators in the 50s, 60s, 70s that all had one refrigerant. Same refrigerant they used in the cars, same refrigerant they used to use in the aerosol cans. So if your grandmother had Aquanet hairspray back in the 60s to do the beehive, she probably had this refrigerant in her can that was used as the propellant. Anybody know what that refrigerant was? 12, R12. Yeah, R12 was after the methyl chloride, sulfur dioxide, which you can't recover those, and they kill you. So when those leaked, they used to have like a bird, and if the bird was dead, they knew to get out of the house. That was like a mine, like a canary in the mine. But so they came out with R12 that was safe. It was safe when it leaked out. It was non-flammable, non-toxic, and they thought didn't do anything to the environment for many years. So it wasn't until the 70s that they started figuring out that they could not use the R12 as a propellant. They could not continue using it in the HVAC equipment and in the refrigeration equipment. So they were going to have to come up with some alternatives. So, but all this slide here is just pretty much showing you heat rise and the direction of heat flow. So, a couple other things about heat. There's two types of heat that we talk about. Sensible heat, and it's going to cause a change in temperature. That's mostly what you feel. So like outside, when you go outside and the wind blows, right, you're feeling that temperature difference. But you also, so we don't have a change of state. Change of state is something different. Change of state is latent heat. So this causes a liquid to boil off in a vapor. So let's say you're in here and you're getting a little warm and you get a little sweaty, right, on your hand, and then you go outside and the wind blows. What's going to happen to that water vapor that's on your hand? It's going to evaporate, right? And the faster the wind blows and the drier the air is outside, the faster it's going to evaporate, which is going to remove the heat from your hand faster. So everybody thinks when you sweat, that's what cools you off, the sweat, because it's water, right? It's liquid. It thinks the liquid's cooling you off. But let me ask you this. What's your body temperature? 98 degrees, 0.6. So what would the sweat be coming out of your body? Same temperature. It's equal. It's even, right? It's not going to come out any colder. If your body's 98.6, the sweat coming out of your body's 98.6, then what makes you feel cool then? The evaporation process. You feel cooling you feel this latent heat cause change of state, and latent heat, when it's evaporating, causes a change in temperature on your body. You do feel the temperature difference. So you got both working. But there's two different heats we talk about. Sensible heat, you can see it with a thermometer. This is what we use to measure subcooling and superheat. And latent heat, this is what we're doing in our evaporator and our condenser. This is how we're removing the heat. Just like that sweat boils off your body, right? We're doing the same thing with the heat. The refrigerant's absorbing the heat in the evaporator, and that's boiling off. And that gas is getting carried back to the condenser, where a change of state will happen again when it rejects the heat. It'll change it back to a liquid. And we'll talk a little bit more about why and how that happens, because everybody's got to kind of understand that concept to really get this refrigeration system down. But we can get it. Before we get there, though, we got to talk about enthalpy. So go ahead and draw yourself a little chart here. You don't have to do a big one. You can do about maybe half a page, quarter page, something like that. But we're going to graph it, and I'm going to talk about two things. We got two sides to this chart. One side on the left, this axis is all going to be temperature. And you only need to know 3 reference points for temperature. We're going to start off at 0 degrees Fahrenheit, and then you're going to go to 32, and then you're going to go to 212. What happens to water at 32? Freeze. And then what happens to it at 212? Oh. Okay, so those are the 2 reference points we got. While you're doing that, I'm going to go ahead and draw a couple things up here on the board. All right, so before we get into this graph, and I explain sensible latent heat, and we graph the enthalpy of water, 1 pound of it, from 0 to 212 degrees Fahrenheit, let me talk to you about the difference between what we're talking about with heat intensity and heat quantity. Okay, because we got a couple terms that we're going to use with that. Now, the heat intensity, think about this. What do you got in the molecule? What do we got down to the atom? Anybody know the parts? Want to do a little science? Yeah, protons, neutrons, that's in the center. And then what's orbiting around it? The electron, yeah. So you got all that down, you figure that out. You don't need to know that much more about it other than that. But you also need to know that this thing's moving around and this thing's vibrating, right? And as it warms up, what do you think happens to it? It expands. Yeah, well, no, it really don't expand, but it vibrates more. All right, it vibrates more. Think about this. Think if you had 10 of these in an elevator, like 10 guys in an elevator, right? And then what happens if you start jumping up and down? You're going to get hot, right? You're going to start to heat up. I mean, and the people in the elevator are probably what? Stand back a little bit, step away from you if you're just in the elevator doing this, right? Doing this. You're going to warm up, and they're going to expand away from you. The people around you are going to move. The same thing happens with this, right? It vibrates more when it gets warmer. It also expands a little bit, right? Or between each other. They start to orbit faster, and they start to spread apart, and that's what makes it less dense, which causes these molecules to rise up over the ones that aren't doing that vibration. They're going down. So let's say I got 2 matches here. So let's talk about that vibration. What's on the tip of a match? What do they call this stuff? Phosphorus. Sulfur. Okay. And they got on the tip of the match the same thing. I got 2 different matches here, though. I got a regular match like you get at any place. And then I got one of the ones for the fireplace. Who's got the fireplace around? You know, you ever seen them? They're coming in a round can. They're really long, yeah. You seen those before? All right. That one there, it's got the same stuff at the end of it as the one that we got regular. If I was to strike these matches, anybody know how hot it would get? What the temperature would be? No, not 1 degree. Not 1. That'd probably be a lot hotter than that, because if I touched it, it'd boil my skin, boil the moisture in my skin. So it's got to be above 212.
340.
All right, we'll say 340. All right, so it's going to get up to 340 degrees Fahrenheit. All right, so they're both probably going to get up, if they're made it and have the exact same amount of material, phosphorus, sulfur at the end, then it's probably going to burn at the same temperature, right? Right? Yeah, it's probably going to get as hot The intensity is going to be the same. But let me ask you this, which one's going to burn longer? A or B?
B.
Yeah, obviously B. So this one might burn about for 1 second, maybe a little bit longer. For about a second though, this one will burn from beginning to end for about 1 second. So think about that match like 1 BTU's worth of heat. So in other words, if I had this match under a pot of water, and the water's on a, let's just say we use the match. We put the match under the water. I have 1 pound of water. That's H2O, water right there. And the water, I put a thermometer in it, and the water reads 70 degrees. It's room temperature water. And I take the match, I strike it, I light it, the entire match burns. What's going to happen to that water? Raise in temperature by 1 degree. So where it started at 70, after I burn that match, the heat will be transferred to that water, raise the temperature of it up 1 degree Fahrenheit. Let me ask you this. I burn this match. This match probably could fit about 5 of those in it, right? 5 of these would fit into the one long fireplace match. So this one's going to burn for about 5 seconds. So think about this as being 5 BTUs worth of heat. And that one there, when I burn it, will cause the water to go, instead of 70 to 71, it's 75 degrees, because it's, so we see the difference. They both burned at about 340 degrees, but because this one burned longer, we increased the quantity of that heat, which raised the temperature. And there's a direct relationship with everything, and its temperature and the amount of heat that you add to it. And not all of it is 1, because a BTU, the short definition of it is what you said earlier, was BTU, the amount of heat required to raise 1 pound of water 1 degree Fahrenheit. So that's the short of it there. So 1 BTU is the amount of heat required to raise 1 pound of water 1 degree Fahrenheit. Now, everything doesn't have that rule. In fact, copper and ice, let's go ahead and start out with ice. Ice can get below 32 degrees. In fact, we talked about low temperature refrigeration being 0 to -20. When ice comes out of your freezer, it's probably closer to 0 degrees right here, or maybe even a little bit colder if you have your thermostat and your freezer set down even lower. So, but ice is a little different. If I wanted to take ice from 0 to 1 degree, I wouldn't have to burn the whole match. With ice, it's got a different, what's called a specific heat value. It's got a specific heat value of 0.5. So when I burn half that match, let's say I'm only going to burn this much of it right here, that's all that's going to be needed to take it up 1 degree Fahrenheit. So the ice starts to go up 1 degree about halfway through the match. And then if I let the whole thing burn, that means it's going to go up 2 degrees Fahrenheit. And they got a fancy formula for it. I'll write it down, but it's not really that important to you for the test. But they got a formula that goes along with it, and you've probably seen it before. They use Q as BTU, and then they multiply that by, they multiply the weight by its value, the specific heat value, and then they multiply that by the delta T, and that's how they figure out how many BTUs they're going to need in order to add or remove the temperature of something, all right, to raise or lower the temperature of something, whatever it is. So for ice, we got to go from 0 degrees here to 32. Because at 32 degrees, if I add any more heat to that ice, it starts to do something. Yeah, it melts. It starts to melt. So to figure that out, from 0 to 32, I would put that right here in the delta T part of the formula. 32 minus 0. That's delta T means delta is difference. Yeah, or change. Some say difference, some say change. And the T is temperature. The specific heat factor will be given to you. There's a book that has everything listed, from apples to every single metal to wood, right? That has all these values listed. And then, so for ice, it's 0.5. And then the weight is 1 pound. So the W is the weight. All right, so we're talking about 1 pound. And the formula of this goes right into it. 1 pound of water, 1 degree Fahrenheit, 1 BTU. Because water has a specific heat value of 1. But ice, we're going from 32 to 0. It doesn't have a specific heat value of 1. It's got a specific heat value of 0.5, and we're still going with 1 pound. So in order to get this, to know how many matches I need to start to melt that ice, they just multiplied 1 times 0.5, that leaves us with 0.5, times 32 minus 0, which is 32. So pretty much you take 32 and divide it by 2. That leaves us with 16 matches. So it's going to take me 16 matches worth of heat to raise the temperature of that ice from 0 to 32 degrees. And because it's raising temperature, what type of heat is that?
Sensible.
Sensible. Yep. So you see that. And it only took 16 matches. And there's the formula we used. Copper, which is pretty common in our industry, for every 1 match, if I let that whole match burn underneath a 1 pound block of copper, or a 1 pound piece of copper, could be a tubing piece of copper tubing, it would go up 10 degrees. Because its specific heat factor is 0.1. So for every 1/10 of the match that burns, copper would go from 70 to 71. And if I let the whole match burn underneath that 70-degree piece of copper, it would turn to 80 degrees just like that in the 1 second that the match burned. Because it's got a different factor. Mercury would go up like 30 degrees if I let the match burn. So if I had mercury at 70 degrees and I let the match burn, it would go up to 100 degrees, just like that. So everything's got a different level for this specific heat factor. Right now we're just going to talk about water. Because we can do something with water when we change the temperature or change the pressure. Which here they change the temperature now. So at 32 degrees, it's not going to go up in temperature anymore. What temperature does ice freeze at?
32.
What temperature does ice melt at?
33.
32. No, at 33, we start to go up in temperature again. That means all the ice was melted a degree ago. So now, not 33, not 32.01, not 30. Once you're beyond 32, we melted all the ice. So it takes 144 matches. I got to add 144 BTUs worth of heat, and they call that the latent heat of fusion, right? Because that's going to be latent heat, because the temperature's not going to change, but the material will. And this is kind of a neat thing, because if I go in the summertime and I get one of those McDonald's coffees, I like a lot of milk in my coffee. And sometimes I got to run into the store and I'll leave the coffee sitting in the car while I run into the store. And it's like 100 degrees outside some days. So I'll come back in, and if I got some ice still in the coffee cup, that means the temperature of the cup and the stuff in it is what? 32 degrees. So could I probably drink that milk and still be all right? Yeah. But if I come back and I don't see any ice in the cup, right, and the cup don't feel cold, I'm probably not going to drink that coffee no more because the milk's probably starting to spoil. But as long as I see the ice right here, I have 50% ice, a 50% ice cube, and then here we got about 50% water, 50% cube right here, right? Right about here. And then here, it melts even more and makes a bigger puddle. And the temperature of the ice is 32 degrees. Temperature of the water around the puddle, now around the edges it might have warmed up a bit, but pretty much what we're talking about is the ice bath. The mixture of the ice water on the water, the ice water, is going to be both 32, 32. And it stays 32 until all the ice is melted. Once we're left with just a puddle, then that's it. We've done change of state, and we're right here. And I add any more heat, I burn any more matches underneath that puddle, it's going to start to do what again? Raise the temperature. And because it takes 1 BTU to raise 1 pound of water 1 degree Fahrenheit, it's going to take 180 BTUs to go from 32 to 212. Because that's the math. If I did 32, 0, 8, 1. 180. 180, 180. It's going to take 180 matches to raise the temperature of that water from 32 degrees, where it's nice and cold, to the point where if I add any more heat, it's going to start to do something else again. So there we are. There's the sensible heat. And I've raised it from 32 to 212 to where we call this line saturated. So I've gotten up to where it's what we call saturated. That saturation means if I add any more heat to it, temperature's not going to go up. In fact, at sea level, you cannot get water above 212 degrees in an open pot. It won't happen. 212 is as hot as you're ever going to get that water in an open pot. All right, and then actually if you add any more heat to it, you're not going to see the temperature going to go up. You're going to see that first bubble develop. And look at how much heat it takes to change it all from a liquid to a vapor. Boom. Takes almost 5 times the energy that it did to go from a solid to a liquid at 144 BTUs than it does to go from liquid to a gas. And then after, if I could capture all this gas, all this steam, we call the water vapor in vapor form, if I could capture all the steam in a bag, or better yet in a pipe, right, and then circulate that steam through pipes, I could even heat up that steam even more. I could go beyond the temperature of 212, but not with water, but water in vapor form as steam. And I could heat that steam up to 214 degrees, right? And when I'm going this way with that water, and I'm heating it up, they call that the latent heat of vaporization. But when I'm going the opposite way, when I'm coming back, and let's say I captured the steam in a bag, or in the pipes, and I blew on it, cooled it down, got it down to 212 degrees right here. If I continue to blow on it, or I get a fan to blow on it and cool it down, it won't lower the temperature, but it'll start to go this way on the line and do something else called condense. So if I'm going this way, that's the latent heat of vaporization. But if I'm cooling it down and changing it back into a liquid, that's the latent heat of condensation. All right, so we're going and we're condensing it. And then I can even cool that water down even more from 212 degrees if I continue to blow on it, and maybe even get that water down to 210 degrees Fahrenheit. This is where the work in the HVAC system's done. The refrigerant absorbs the heat in the evaporator, causes that refrigerant to boil off. We take that and suck it back through a compressor, and then the compressor pressurizes that refrigerant and pushes it into a condenser where the heat's rejected, and then we actually cool that liquid down a little bit more. And what do we call that extra coolant? That coolant below this saturation line. Anybody know? Yeah. Saturation. All right, subcooling. That means we've subcooled this water by 2 degrees. Because it's 210, that's 2 degrees below 212. That means we've gone 2 degrees of subcooling. We've subcooled that liquid 2 degrees below its saturation temperature. And then if I continue to throw it back in the evaporator, boil it off, and then heat up all that boiled off gas, maybe to 214, that's extra heat. What do they call that extra heat?
Superheat.
Yeah, superheat. All right, so that's superheat. So actually I've gone with about 2 degrees of superheat above the boiling point. So that's where all the work's done in the HVAC system. Where they size up the equipment is right here. You hear the word tonnage thrown out a lot? No, I worked on a 10-ton unit. Oh, this building's got a 100-ton unit. Yeah. Well, what do you need for your house? Maybe a half-a-ton unit. Some of you got a 3-bedroom house. You probably got a 3-ton unit. What are they talking about with that? They're talking about the capacity, the system's ability to melt or make a 1-pound, or in this case now, 2,000-pound block of ice in a 24-hour period. Because that's how many pounds are in a ton, right? 2,000? So how many matches would it take to melt a 1-ton block of ice? How could I figure that out? Well, how many pounds did we say were in a ton?
2,000.
Yeah, okay, so 1 ton equals 2,000 pounds. And then, well, how many BTUs did it take to melt 1 pound of ice? 144. So if I take 144 and I want to figure out how many matches I got to do a ton of ice to melt a whole ton of ice, I'm probably going to multiply that by 144, which is going to equal 288,000 BTUs. Right? So if I wanted to melt a 1-ton block of ice, that means in a 24-hour period, I would have to stand here with matches and just keep lighting them and letting them burn underneath that ton of ice, and eventually in a 24-hour period, it would melt. Right? So if I take it and I divide it, I want to see, man, how many matches am I going to have to do an hour to burn that 1-ton block of ice? I'd go, well, there's 24 hours in a day, and I got to do 288,000 of them. Well, that's 12,000. So in order for me to melt a 1-ton block of ice in a 24-hour period, I'd have to burn 12,000 matches worth of heat an hour in order to do it. They call that BTU per hour. And that's where they get the tonnage from. So if they tell me that they have a 2-ton system, that means that 2 tons, if 1 ton can do 12,000 matches in an hour, then that means a 2-ton system can do 24,000 BTUs worth of heat. in an hour. And then 3 ton would be 36,000 BTUs. 4 ton would be 48,000 BTUs. 5 ton would be 60,000. Now you got a model number on the side of your air conditioning unit in your house, whether it's a window unit, through the wall unit, outdoor unit, package unit, you got a model number somewhere. And on that model number, it might say something like CK024, that 1 or something. You want to look for the number that divides into 12. And sometimes it doesn't divide into 12 easily because they not only have a 2 or a 3 ton unit, but they got a 2.5 ton unit. They got a 1.5 ton unit. And those are in 18,000 BTUs, 30,000 BTUs. So you might have a number that's like 30 or 18 or 42. They don't really have a 4.5 ton unit. They just go from 4 to 5. They figure if they're going that size. And then from 5 it goes to 7.5, 10, 12.5, 15, 20, 25, and then they just keep going from there. And all they're doing is they just keep adding more compressors or making the coils bigger and making the compressors bigger. That's all they're doing. It's the same system as you might have for your refrigerator. Compressor, condenser, meter device, evaporator. Just everything's bigger, and they use some different controls and some different floats, some metering devices to handle the larger amounts of refrigerant. But it's all pretty much there. And then if you like, well, what size? Well, I think I heard my window unit went out, and I had a 1/2 ton in there, and it's just for one room, right? Because I'm trying to just cool my space. I'm just renting a room. What size unit? Is that the right unit? Should I get another unit the exact same size? You know, it never felt like it cooled all the way. It was a 1/2 ton unit. And I got a big room. I'm in a loft. Let me see here. Well, you got to do some math. And there's a rough rule of thumb to let you figure out, without doing a load calc, the real right way it's supposed to be done, right? Looking at all the windows and doors and insulation and everything. But there's a rough rule of thumb that a lot of people use that's a little bit better than the Sears method. Sears used to stand out the side of the house with a piece of cardboard, and they had 3 different house cutouts. And if they were about at the curb and your house fit in this cutout, that meant that you needed a 3 ton unit. If your house didn't fit in that cutout, then you needed to go up 1. That meant you needed a 5 ton unit or something bigger, you know, a 4 ton unit. And if your house was too small, then they went down to the smaller one. Oh, that was a 2 ton unit. That's how they used to size up some equipment back in the day. That's how they figured it out. And I don't know how accurate it was, but this might be something just as accurate as that. But it's a rough rule of thumb that a lot of people use. They say usually with old construction, 1 ton of air conditioning can cool about 500 square feet. With newer construction, it's a little bit more, maybe 600. And then with really old homes that don't have any insulation, it could be a little bit lower. But roughly, everybody goes with about 1 ton of air conditioning can cool about 500 square feet. Now, if the whole thing could be windows, it's going to throw that off. All right, if you're living in a corner unit with both sides covered with windows. All right, but 500 square feet. So let's say you got a space that is 30 by 25. That's pretty big. You know, 30 by 25, and you wanted to replace it with a 1/2 ton unit. Well, you would need to figure out the square footage of your house, multiply the length times the width, and figure out what the square footage is, the area, all right, and then divide that by 500. So 30, 10 times 25 is 250. So that's 750, right? 750 feet, square feet, all right? 3 times 25, 75, put the 0 at the end, that's pretty good. So divide that by 500, what should the equipment have been?
1 ton.
1.5 at least. Yeah, maybe 1 ton. You probably could have gone. But yeah, and that's about the size, the max size. Maybe 2 ton heat pump you might be able to get for a window unit. It's pretty expensive. But that's about the height, the size, the max size of a window air conditioner. Before, when you go into these, you have to start getting a package unit or a through-the-wall unit or a unit that has what we call split system, which has lines that you got to braze together from the indoor to the outdoor and do leak checks and stuff to make sure it's not leaking. So, but that's some little bit of stuff there, all right, related to the sizing of the equipment, where they get it from, on this enthalpy. So now what you've just done is enthalpy is a fancy word for heat content. So we've gone from 1 pound of water at 0 degrees Fahrenheit, and we added 16 BTUs to get it to start to melt, or get it to the melting point. And then we added 144 BTUs to melt it. We added 180 BTUs to raise it to where it's going to start to boil. And then it took 970 BTUs to boil. And that's it. And then if I wanted to add one more BTU worth of heat, it would go up ice and steam, pretty much neck and neck. 0.5 on the ice, 0.52 on the steam for the specific heat factor. So when I add 1 BTU worth of heat, it's actually going to go up to that 214 mark. So the total amount, it took 1,300 matches, almost a little bit more, to go from 0 to 212 degrees steam with that 1 pound of water. Any questions on that?
That's in BTUs, the 1,300.
That's in BTUs, yep. Everything on the bottom is BTUs, per hour. So there's a time limit to it too. It's not just, you couldn't take all day to do the 16 matches. We're talking about over a period of per hour. So, now look, these numbers, freezing and boiling points for the water, this was all at sea level. You go to Denver, it's not going to be 212. No, it's not going to be 212. Let me ask you this about Denver. Let me go ahead. Everybody got this? I can erase this now? We're good? We're getting ready for a break. We're going to break about 10:30. What time are we at now? My alarm will go off. 10:08?
10:08.
All right, so we got about 10 more minutes. Those of you bear with me. They've been sitting here since 9. But let's talk about this real quick. We'll get this concept down, and then we'll see where we're at. So right here, I'm going to draw the world. And then that's brutal. Let me at least get Florida in there. All right, and then, okay, all right, that's it, okay. We're here in Washington, D.C., right? That's us. We're pretty much at sea level almost. We're a little bit above, a few hundred feet, but we're pretty much at sea level. So at sea level, water boils at 212 degrees Fahrenheit. And that's because at sea level, air's got weight. They used to do an experiment with balloons. They'd fill up a balloon twice as big as another balloon and let you drop them and let you weigh them and stuff like that. 1 cubic foot of air. That's 12 inches, like that about that, that about that, that about that right there, About a cubic foot of air weighs 0.07 pounds. And then if I had 13.33 by 13.33 cubic feet, right, at 70, 75 degrees, that would also be 1 pound of air. So 1 cubic foot is like 7/100ths of a pound. Really, really small weight, small amount of weight, right? But it does have weight. Air's got weight. 79% nitrogen, 21% or so oxygen, and then some mixed gases in there. But it's got weight. And it takes about 13 cubic, which is about 2.5 by 2.5 by 2.5, right, for it to equal 1 pound. And you would be surprised at the amount of weight of air in this room if we took the volume of the room and multiplied it by the 0.07 for each cubic foot, right? It'd be 200, 300 pounds. You'd be like, 300 pounds of air in this room? Yeah, there is, but it's spaced out, so you don't really see it, right? So that air's got weight, and let's say instead of a cubic foot, I'm going to go with something like this, a cubic inch. And I took that cubic inch, and I started here at sea level, and I could weigh that. Let's say I made some sort of chamber that was 1 inch square, and I took it all the way up to the stratosphere, which is roughly 10 to 30 miles above the Earth, right? Because you got the troposphere, which is up to about 6 miles. That's the air that we breathe, right? Up to a point. That's all the oxygen that we breathe. And once you get above 6 miles, even a little bit lower than that, but 6 miles, the air really starts getting thin. And that's where you're starting to get into the stratosphere. This is where the ozone is. The ozone is up in the stratosphere. This is where they figured out the hole was, up here above the pole. And that means that it didn't have all the O3 molecules that it needed, the ozone, oxygen times 3, right? And it didn't have all those molecules up there, and that's where they figured out that the hole was a problem. But air right here, if we took it with that 1 inch column, would have a certain value. It would weigh up to a certain amount of pounds at 1 cubic inch from sea level all the way up to the stratosphere. What would that weight be? Anybody know? They mention it in the book a couple times. It's called atmospheric pressure.
Oh, 14?
Yeah, 14.7. 14.7 pounds. So that 14.7 pounds is what we call the absolute pressure or atmospheric pressure, right? And then if you were to go lower, let's say you go down the metro or go a couple miles down, that pressure would go up because you have even more air. But over here in Denver, what's the name of Denver Stadium? Yeah, because they're about 5,280 feet. They're a mile. They don't have 6 miles or 30 miles of air. They got 29 miles of air above them. They're missing a mile of air because they're a mile higher. They're a mile higher than we are. So are they going to have 14.7 pounds? Nah, they only have 12.5 pounds of air, right? Their air's lighter. In fact, those football players, some of them had to go out 2-3 days beforehand, especially the bigger guys, just to get adjusted to that difference in pressure, right? And that's because the air didn't have the same weight as like LA or over here on the East Coast, because they're not down at sea level anymore. They don't have that same pressure. And then you get up even higher into an airplane, right? You get into a jet that's going 6 miles above the earth. What's the first thing they got to do before takeoff? Pressurize the cabin. You feel that difference in pressure. You feel it when you got to chew your gum or you hold your nose and you're trying to do what? Pop your ear, because behind your eardrum you got a little bit of fluid. And at 14.7 pounds, it feels normal to you. But as soon as you start to go up and this pressure starts to drop, that fluid does what? It starts to expand out a little bit, because it doesn't have the same amount of air pushing this way. And then when it expands out, that causes some discomfort with you, and you're trying to pop your ear to adjust the fluid. All right? And that's what you're doing with it. You could feel the difference in the pressure when you're on a plane and you take off. So the pressure is going to be different. Well, guess what? The boiling point's different too. Water doesn't boil at 212 degrees when there's only 12.5 pounds of air on top of it. It boils at a lower temperature. It boils at like 205, 207 degrees. And then if I was to take it up to 6 miles into the atmosphere, like let's say there's only one place really in the earth that goes almost that high. That's over here near Nepal. What is that, Mount Everest? Right? 30,000 feet, which is about 6 miles, between 5 and 6 miles. If you go to YouTube, you can actually see a Nepalese man running up the mountain with a propane tank and a pot of water. And he shows you that the boiling point when he's starting out at sea level, down at the base of the mountain, base camp 1 or whatever it is, he's showing you that it boils at about 212 degrees. And as he's going up the mountain, he's got his thermometer in the pot, he's pumping up his little propane grill, and he's boiling the water at lower and lower temperatures until he gets, I don't think he goes all the way up to 30,000 feet, but he goes up to a higher distance, and he's showing the drop of that pressure-temperature relationship, that boiling point dropping because of the air pressure dropping. So there's a direct relationship there. In fact, so this 212 number is dependent on the pressure. It can. Everything moves up and down. The freezing point lowers. The boiling point lowers if we lower the pressure. Or if I wanted to raise all that, I could raise the pressure somehow. In fact, your grandparents used to use that method to cook their food faster. I'll talk about that in a minute. Any questions about this stuff? Or atmospheric pressure? We need to know that, because what we have going on in the evaporator is the bulk of our work. That refrigerant is a liquid, like liquid on your skin, and it boils inside the copper tubing, just like the sweat boils off your skin, and it carries away the heat, because the heat's absorbed with that boiling process. And then we take it and feed it into the condenser, where we reject it, and that heat changes, that refrigerant changes with the loss of heat back into a liquid. So I'm just going to show you this real quick. So this is like the match example. It's going to go up 2 degrees with that full match burn. Go from 30 to 32. 1 BTU will raise ice 2 degrees. But water, one match does 1 degree. So it's got to take 144 matches to melt the 1 pound block of ice to water. We're going to change temperature. Once it's all melted, then we can change the temperature. And we want to raise it to 212, so it's going to take 180 matches to do that. Then it's going to take another 970 BTUs worth of heat to boil all that water into steam. And then I'm just showing you one last time, but I think you got it. To condense it. So let's say I captured all that steam in a bag up here, right? And it's 212 degree vapor. Now I haven't raised the temperature, but it's it. We got no more liquid. And if I heat it up anymore, now the temperature would rise. But let's say we're not going to heat it up. I'm going to cool it down and blow on it. And I blow on it 970 times. That means every time I blow, we're getting a little bit of water back into the pot. We're condensing it. So we're doing the opposite of adding the heat and boiling it. And we can just keep doing that. And then if I was to continue to blow one more time or 2 more times, temperature would drop another degree. And that extra temperature drop is what we call subcooling. The water's now subcooled. And you can use these pressures and temperatures without looking at the water to tell me what it is. If it's a liquid, if it's saturated where it's boiling or condensing, depending on if you're adding or removing heat, or if it's all vapor. You can tell me with a gauge and a temperature measurement. And you know if it's below the boiling point, if we're below 212, it's got to be all liquid because it's subcooled below the boiling point. So it's subcooled liquid. If it's at the boiling point, 212 at sea level, that means we're going to be both mixture of vapor and liquid. We call that saturated. That's the fancy term they want to use for that. And then above the boiling point, if it's 213 above or anything above 212 really, that means it's superheated and it's all been boiled off to a vapor. So again, looking at a pot, say you could not see inside the pot, and we're looking at a thermometer here, and we see it's 211. What does that mean? Superheated? Is it now? Forget about superheated. Let's just see if you know at 211, is it going to be a vapor, a mixture of both, or just a liquid?
Both.
Okay. What temperature does water boil at?
212.
Is it at 212 yet?
No.
So is it boiling yet?
No.
So what does that mean in the pot?
Liquid.
Liquid. There we go. It's all liquid. Yep. And it is subcooled liquid because we're below the boiling point. Now, say you took it away again and you couldn't see, but the temperature's at the boiling point. That means you got either vapor liquid, or liquid.
Vapor liquid.
Yeah, that's saturated. When you see that you're at the boiling point, we got both vapor and liquid happening. And then if you're anything above 212, I think you're seeing the pattern now. We're at 213, that means we got what in the pot?
Vapor.
All vapor. And it's not just any vapor,
Super.
superheated vapor. Yeah, there you go. You got that down now. So that's that. Cooling, they'll have this on a slide. They'll talk about it. It's just refrigeration is the removal of heat. We're taking the heat from in this space where we don't want it, and it's going to cause that to melt. Temperature will drop, and we take it to a place we don't care about it. So heat, removal of heat is just cooling the surrounding air. We're absorbing the heat by removing it from the air, and they call that cooling. Anytime you take away the heat, that's a process of refrigeration, process of cooling, same thing. This is going back to that 144. I don't need to really, I've already hit it. All right. I think we're pretty good. It's about 10:30, almost, maybe 10:20. Let's go ahead and take a 10-minute break real quick, get a drink if you need to, walk around, use the restroom. Just some things